to hours of a day. The slides for this presentation are available to the public and can be found at the URL listed first. The second URL gives a dashboard where the analysis for the presentation takes place. Little background on co-op wholesale power costs. Overall, the wholesale power costs typically range from 45 to 55% of the co-op's total expenses. At GVP, where I'm a board member, the power costs are currently around 51%. The costs fall into three categories: fixed costs, energy costs measured in kilowatt hours, and demand costs measured in kilowatts. The last item is going to be our focus. Okay, to understand what demand costs are, you have to understand what demand is. Demand is essentially the rate at which the energy is used. Energy is measured in kilowatt hours, divided by the hours that consumption takes place in, and you end up with your demand. You can consume the same amount of energy over a short period of time or a long period of time. The short period leads to a high demand, the long period leads to a low demand. The graph that's shown here is June 2023, and the blue dot represents the highest demand for that entire month. The demand charges then are to take the value of that demand at that point and multiply it by the rate that your wholesale supplier has set with you. And so that would be a rate in terms of dollars per kilowatt. And it can be substantial. Here in this particular figure, you got 50,000 kilowatts, and you multiply that, let's say, by $15 a kilowatt, and you get a large number. Okay, so why do you need to know how to split up demand costs across hours? Well, if you're developing any sort of rate tariff that is time dependent, you need to know how the costs can be distributed to the time, how they vary in time. For example, maybe you're looking at something where a tariff that's focused on rate shaping. You would need to know when the peak hours for charges are. Those charges have demand costs. How do you distribute it from that one peak of the whole month to the hours? Maybe you have a motivation of fairness. Cost causers should be the cost payers. Well, then you have to figure out when things cost more than other times. Maybe you want to figure out a EV tariff, and you need to know when would be a good time to do this. When to offer, let's say, a discount for EV tariffs to encourage people to charge their EVs when the costs are lower. Or maybe you have a tariff with a time-dependent demand component. Some co-ops in Colorado charge demand in a particular time frame on consumers' bills. So you need to know what is that demand at a particular hour of the day. All of these things require knowledge of power costs by the hour. A little more background on demand charges. The grid infrastructure is designed to accommodate the maximum peak demand. That infrastructure could include, or does include, transmission capability and also generation capability. And so the question is how to spread the costs of putting that infrastructure in place over a period of time in a way that makes sense. So demand charges were conceived as a way to spread that cost over the useful life of the asset, whether that asset is being used at full capacity or not. Okay, so we've got our formula for demand charges. Take the peak hour of the month, multiply it by demand rate, you get your charges. Now, if you're actually trying to do some load shaping, you might ask the question, what hour of the month is going to be the peak hour? And I'll tell you that it's as predictable as the weather, meaning it's hard to figure that out. But you can study it and come to some sort of predictions on this thing. But even if you knew when that hour was going to occur, it doesn't tell you anything about other hours. You really have to get into this thing and study it to find out what other hours are high and low. Knowing just the peak hour doesn't give you enough information. And for example, you want to charge for your infrastructure, which is being used at all different levels at all times. And so how do you do that? That's what we're really going to be looking at. But also, there's this idea that since it's based on 1 hour, that's the only hour with demand charges and everything else is zero. Is that right? It seems that that would be a bit strange. Okay, so we've got our formula for demand charges. Take the peak hour of the month, multiply it by demand rate, you get your charges. Now, if you're actually trying to do some load shaping, you might ask the question, what hour of the month is going to be the peak hour? And I'll tell you that it's as predictable as the weather, meaning it's hard to figure that out. But you can study it and come to some sort of predictions on this thing. But even if you knew when that hour was going to occur, it doesn't tell you anything about other hours. You really have to get into this thing and study it to find out what other hours are high and low. Knowing just the peak hour doesn't give you enough information. And for example, you want to charge for your infrastructure, which is being used at all different levels at all times. And so how do you do that? That's what we're really going to be looking at. But also, there's this idea that since it's based on 1 hour, that's the only hour with demand charges and everything else is zero. Is that right? It seems that that would be a bit strange. Okay, our goal here is to figure out how to distribute a charge that's based on 1 hour out of the month, how to distribute that across all hours of the month. I'm going to define equitable here as paying for your share of the system usage while you're using power. At a high level, these are the things that I hope you take away. 3 things. 1, method. I hope you understand how demand charges can be distributed over every hour of the month. 2, I hope that you gain insight as to the hourly distribution of wholesale costs. And 3, that you have an understanding of a framework that can be used to inform decisions when you take hours of use into account in a tariff. As we proceed and develop our method here, we're going to be looking at 2 curves, the hourly demand curve and the monthly duration demand curve. They actually contain the same information, but they're presented in a different way. The hourly demand curve is a time series of system demand. We've seen that in the June 2023 curve that's been shown, but we're going to take it and rearrange the data in that curve to be ordered by demand, not by time. And that's what the monthly duration demand curve is. Here's a monthly demand curve. This is the one we've been looking at, June 2023. And you can see that it's ordered by time as we go across the x-axis. Each peak in June typically represents the evening hour in our area where this is taken. Air conditioners are going more often, and so there's more demand. This is the monthly demand duration curve for June 2023, and you can see it's very different. Along the x-axis, what you have is percent of hours in the month. So what we've done is we've reordered the hours by their demand, and so it's going to be a decreasing curve going from the maximum demand to the minimum demand in that month. To help you understand how these 2 curves are the same, I put together a small animation for you. What I'd like you to do is to focus on these top points. They move horizontally to the left, whereas the bottom points actually move horizontally to the right. Here goes the animation. And there we are at the monthly demand duration curve. Okay, here is the monthly demand duration curve that we're looking at. The peak demand time is on the left, and the minimum demand time is on the right, and we're going to use this curve to try to understand how to distribute demand costs across all hours. Okay, in order to distribute the costs across every hour, I'm going to have to make some assumptions. My first assumption that I'm going to be working with is that the hours of similar demand should have similar costs. This is what's called a continuity assumption, that small changes in demand should not drastically change the hours demand charge. The second assumption is that the base load, and we'll talk about what that is, contributes to demand charges. We're first going to deal with the concept of hours of similar demand should have similar charges. And I'm going to do that by focusing on the peak in June of 2023, and you can see it here. It occurred at 1800 hours at June 26. It's the red dot, and you can see nearby that there are other points that are close to it. Here I've blown it up just a little bit further so we can see that The 1700 hour is here, the 1800, and the question is how to take the charges that are dependent on this one and spread it, let's say, over other points in this picture. What I've done here is I've drawn a green horizontal line from the second highest point in the month across to the highest one. You might ask, what's the difference between that peak and the second highest point? Turns out that in this particular month, the difference was 566 kilowatts. Now, when you multiply that by your rate of being charged, that could be $9,000 to $10,000 in difference. So it is substantial. Now, what happens if we take that red dot and through some load shaping, maybe turning on batteries or something, we move that down to the green line so that the highest points are actually two, they're tie. In that case, I think it'd be very reasonable to split the demand cost 50-50 across both of those points. Let's do the following thought experiment. Let's say that we can control where the red dot is by load shaping. We can move it up and down. If we assume that all the costs were assigned to 1 hour, then the red dot would initially have 100% of those costs. As we move the red dot down, when it got to the green line, it'd be 50-50 sharing between the two ends of the green line. And as we moved the red dot below the green line, suddenly all the costs would jump over to the 1700 hour. So if we want hours of similar demand to have similar costs, then demand in 1 hour will not work. This violates the continuity assumption that I've made, that small changes in demand should only lead to small changes in demand cost. Let's turn our attention to baseload. So here I have the monthly demand duration curve, and I've highlighted the baseload. That's determined by the rightmost point. And it's basically the demand that is there all of the time. But I want to ask the question, what happens if you wave your magic wand and all the demand is only baseload? So this whole top area disappears. Well, the answer is your demand charge does not disappear, it just gets reduced. Here I've highlighted with the red line the demand that is present for the baseload. In June of 2023, this was significant. 36.8% of the demand charges were related to baseload. So I think we can conclude that the baseload has a significant demand charge component. But the real question is, how should we distribute this demand across hours? Well, the natural answer is to assign each hour of the month an equal amount. So what you end up doing is perhaps taking the demand for the base load, the costs of that, dividing by 720, and you end up with a minimum hourly cost. At GVP, each month has demand related to base load. In June, July, and August, it can be around a third. In March and April, it can be slightly over a half. In the last GVP cost of service study, none of this baseload demand cost were attributed to off-peak hours when they were considering time of use tariffs. This brings me to what I'm calling the shared model. Every hour at every kilowatt level receives a share of the cost at that level based on the number of hours that utilize that kilowatt hour level. Basically, this comes from two observations. One, if there's a tie for the peak, you divide by 2. 2 hours, divide by 2. If you are looking at base load, you end up dividing by the number of hours in the base load. We've examined what happens at the peak with 2 hours and the base load with every hour, but what happens when only 50% of the hours utilize a particular level? Here you see the two curves. One is the monthly demand curve and the other is the monthly duration demand curve. And what I've done is I've drawn a red line at the 50% level on the duration curve. All hours that are represented to the left on this red line utilize that level. You can see them over on the time series over here. What do you do in this situation? In the shared model, you take the cost at that level, which is the same at any other level, but you now divide by 360 for June, instead of the 720, because only 50% of the hours utilize that level. And so you include in each one of those hours that portion of the demand cost divided by the number of hours that we're utilizing that level. We can look at the costs at any particular level in terms of what it costs related to the base load. So if we have a level that occurs in 50% of the hours, the cost would be twice the base load. If it's in 25% of the hours, it'd be 4 times, because 1/4 of the number of hours use it. 10% of the hours, 10 times. 1%, 100 times the cost per hour for base load. And if you're looking at strictly the peak hour, that's going to be 720 times a base load hour. Another way to look at this is a base load hour is a little bit over 1/1000th of the cost of the peak hour for a 30-day month. So how does our assumption about similar hours of demand having similar costs work out in the shared model? What we have to do to find out the cost of that hour is add up all the costs for all the demand levels in that hour. It's different for every level as we have different sharing going on. And so what we see then is that these 2 hours that we've been focusing on for similar demand, that below the green line, they have exactly the same shared costs. Above the green line, the peak hour gets all the costs. So what happens is the difference between hours with similar demand really only differ by the extent of that demand difference. Below the green line, the costs between the 2 hours are the same, but above the green line, the difference in cost only amounts to the difference in demand times the rate. What kind of formula does the shared model give us for how much the demand charges should be? First, it's important to realize that every kilowatt level costs the same. Second, that the cost of the kilowatt level is distributed across the hours. That's what's making the difference. And so when we look at the formula, what we get is the peak hour times the demand rate is our demand charges. So we get exactly the same formula that we have on our wholesale energy bill. Let's apply the shared model to an entire month. For June of 2023, this graph kind of represents the demand according to the hour of the day. So what we're doing is we're looking at every single hour in the month, calculating out what the demand was in the shared model, and then adding up all of those hours and presenting it in terms of the hour of the day. So for June, what you have is 12% of your demand was at 7 o'clock. And somewhere in the neighborhood of 2% of your demand occurs in your early morning hours. And then what you can actually see here is you got people waking up and the air conditioner's turning on, starting to turn on a little higher as people come home from work, and then sun sets and air conditioning is no longer needed. That last picture was for June 2023. March of 2023 shows you a very different picture. You don't have the air conditioning going on, you have very little heating going on at that point in time, but what you do see is that your early morning hours are a little more expensive, and you go up to probably around 9% for your 8 o'clock hour, drops down during the day, and then you get a little bump as people come home from work as you go along. You might be tempted to compare this 9% with 12% on the other graph from June. However, what you have to keep in mind is that June uses a whole lot more electricity than March. So this is percent of the total costs for the month. On the previous 2 slides, we're looking at just the cost of demand. On this particular slide, we include not only demand, but also energy, and I've got some numbers at the bottom. You can, on the dashboard, enter whatever numbers you want, but when you're actually trying to figure out how much energy costs at a particular hour, you need to include both. And so here you have the same type of curve here, where it gives percent of the total cost of June attributable to 1 hour. but we're including both demand and energy. One other thing to note here is that in these graphs, we're using standard/daylight hours, so the hours that people live. These monthly demand profiles, as I'm calling them, give you an idea of what's happening in a particular month. So if you change something and you're doing this over a long period of time, you can actually go back and check several different Junes and say, once, how do things change? But of course, when you're setting a tariff, you're not setting it by the month, you're setting it annually. So let's apply the shared model to all 12 months, combine them into an annual profile. Here's an example where you're looking at the demand, and what you get is a distribution of your demand taking into account every single month of the year. In this particular example, it's the year 12 months starting May 1, 2023. You get what you expect, basically. People are waking up in the morning, 7 and 8 o'clock, the demand goes up, turn on their coffee pots, you get some higher demand for power. It goes down during the day. This could be a result of some of the DG customers producing solar. And then as people come home, the summer months start to show up here where you get your demand coming in from your air conditioners. Sun goes down, away you go, back down to your more early morning hours. Okay, let's actually add in the energy cost now. So for the same 12-month period as the last slide, what we see here is where we've taken demand, we've assigned it a cost, energy assigned it a cost, and now our graph is giving us how the cost of energy is distributed by the hour over the entire 12-month period. While this graph gives us a distribution of the cost by the hour of the day for energy, it's really not what we need to actually say how much energy costs. Energy is generally charged by the kilowatt hour to the member, so what we really need is something that tells us about the kilowatt hour cost for each hour. Since our monthly demand curve is hourly, the demand is actually equal to the consumption in each hour. So we can use that to calculate out what the relative cost per kilowatt hour is of our energy that we're importing from our wholesaler. And this is what you get. And so let me just explain this a moment. The green line corresponds to the average cost across the entire year. In the hours that are above the green line, the cost is more than average. In the hours where the blue dots are below the green line, the cost is less than average. And so you can see here that the cost range is from 90% in the early morning hours to about 22% more in the peak demand hours in the late afternoon, early evening. So this is what I'm calling the annual wholesale cost framework. When you have this graph that tells you what the price of a kilowatt hour is, that takes into account both the energy and the demand, you can start to do things with it. It gives you the information needed to distribute power costs by the hour. It gives you the information needed so that you can make choices which can be informed. I have 4 applications here. You can probably think of others, but the applications I'm thinking of is perhaps you're looking at time of use rates, DG production and avoided costs. Maybe you're looking at creating an EV tariff, or perhaps you just want to compare monthly and annual profiles so that you can understand how changes you have made actually have had an effect. Okay, that ends the first part of the presentation. And I'm looking back at my takeaways, and I'm hoping that you're taking away one, a concept of method, understanding how demand charges can be distributed over every hour of the month, even though the actual formula only uses the peak hour. I hope you've gained better insight into the hourly distribution of wholesale costs, and also that you understand that there's a way to produce a framework to inform decisions. You don't have to rely on other people. Just on what you hear, you can actually go off and have someone calculate a framework that can be used to inform decisions when you need to take into account the time that power was used. So what I'm going to do next is to take a look at the dashboard that I've made where you can enter your own numbers, play with things, and I'm going to review what's on each tab, options that can be set, and then take a look at one application of the framework. And the application I'll look at is where is the subsidy with net metering and how large is it. Moving to the dashboard here, you've got the tabs across the top. And the first introductory tab just kind of explains what's here. The power costs explains the shared model, and you can see some familiar graphs showing up here, both the demand curve and the duration demand curve. On the left, it explains what's going on in the model. In this shared demand tab, you can take a look here, and what you can do is choose a month, and whichever month you want to pick. And so let's pick a July. And then you can start moving that red line as to where you want it. You can see that I moved it up to the 20% level right here, and then it displays the hours. So if you wanted to know where the top 1% of the hours are, you can see those. It's like 7 hours right up here at the top. Another thing on this page is this chart at the bottom down here, which tells you where those hours occur at. So you can get an idea if you're looking at load shaping where those hours occur at. Look, as I said in the presentation, knowing only the peak hour is insufficient. You need to know when your demand is. The monthly profile tab gives you the monthly profiles that we were looking at before. You can choose a month. You can set your demand rate and your power rate. And if you're considering something like a time of use, you can change that around a bit. And you can say what happens with a particular time of use time frame. So if you're looking from 1,500 hours on, these times up here are inclusive. So you're looking at these guys here. And then off on the side down here, you see how much of that power cost for that month correspond to on-peak and off-peak. The annual profiles tab does the same thing for annual costs. Over here that we've looked at, you can set in, choose a year, again, your demand charge, your power cost charge. You can pick an hour that you might be thinking of doing something like on-peak, or maybe you're looking at solar and you want to know about net metering type information. One tip here is net metering information is generally given only in standard hours, and so you need to switch this. You get a slightly different curve down here, but if you're looking at least in our area, the solar production window is probably 9 to 8 in standard hours, and so you're looking at this time frame. And what you see is that if you're looking at the cost of your power in that time frame, 57% is in the off-peak time or outside that solar window, and the rest is on that on-peak time. But you also see over here the relative cost per kilowatt hour, and you can see that with your solar, for example, I've got it set up that way. You see that sometimes you're producing where it's less than average, other times you're producing where it's more than average. One other option on here that you can select is this what's called peak demand hour model. That is where all of the demand is attributed to 1 hour, and this is the type of shape that you get. What this is useful for is saying, okay, if I want to set hours, I might go in here and say, okay, let's make those hours from let's go 4 o'clock to 9 o'clock. You can start to see then where the peaks happened and how many of them and what the share of the demand or the cost is for those particular hours. So maybe you want to target some hours as you go along and you play with that to figure it out. All right, the application I want to look at is at net metering, and you set the parameters actually on this page, and then you go over to the next one to see what it says. So I'm going to look at the shared model. I'm going to use just my default system demand charges and wholesale power charges, switching over to the net metering tab. And this one takes a little bit of explaining. Oftentimes when someone's putting in solar onto their roof, what they want to do is produce 100% of their power. So that's where this slider comes in. If I move it down to 0, that means they're not producing any of their power. Let's just take a look at that first. Looking at this annual consumption and production curve, you notice that the green and the salmon colored lines are actually mirror images. This graph's a little bit weird in that it has a positive axis going down and a positive axis going up. If you had this curve on the top, it would lie exactly on the green curve. But if this person is not producing any power through solar, then this is what the system sees as his consumption. And then let's say what happens if they want to add some solar to it and produce 100% of their power. This blue line, blue dots, then gives the annual solar production in a particular hour. That information comes from PV Watts at NREL. They have hourly data that you can then collect and then summarize. And so what you get is this line for production. Now the green line is the net power. You're consuming here, you're overproducing in the middle of the day, and then you begin to consume power again on this side. The middle graph here corresponds to how much that power would cost the co-op if they had to buy it. All right, let me set this back to 0 again. What you see in the middle graph then is the percent of the cost of their power distributed by the hour. So if you would ordinarily spend $1,000 on this person's power, then 4% would be for the 7 o'clock hour. 6% would be for the 1700 hour. Now when we add net metering or solar production into this, then that graph in the middle changes quite a bit. What we have is importing power through here. You actually have to buy this power from the wholesaler, and then that person's exporting power through here. So it costs money here, but it's actually saving you money here because you don't have to buy power for someone else who's consuming it at that moment. Now over the whole day and year, what happens? Well, if they're doing 100% of their power, then what you see is if you would have spent, let's say, just make it easy numbers, $100, you're actually now gaining $1.04 as far as the cost of power goes. However, there's another twist to this whole thing, and that is what I'm calling grid dependence. And that means that that solar user, of course, cannot produce power at night, and they're importing from the grid. And when you take a look at the percentage of time that they're importing power from the grid, you get the grid dependence. And in this example, it's 53.7% of the time they're importing power. Or actually, I should say, the amount of power that they're importing is that much. And that's not taking into account anything about being banked, it's just coming from the grid. And so that power that's being transmitted in from the grid actually typically costs the co-op something because they have to maintain the delivery system. And so if you're looking at this and say, how much power are they actually importing? Well, the way that I can calculate that out comes out to basically if they're looking at 100% replacement, and you calculate out the size of their solar array, kilowatt hours DC, then what you could say is how much are they importing per kilowatt hour DC. So my own solar system is a 4.6 kilowatt DC installed system, and so I multiply this number by 4.6, and that's how much power I would be importing from the grid, whether or not that power was banked with net metering. And this is where I believe the subsidy is for net meterers. It is not in the cost of power. Your company's actually making money there. If they over-install their system, let's say by 120%, that number starts going up. Now, you have to decide what you're going to do with that overproduction, but if you do nothing, then you're making $21 on that guy, if you would have spent $100. But you're still, down here, supplying power to that person when they can't produce their own. That brings me to the end, but perhaps you have questions. If you have questions, you can reach me at gary.deyoung@gvp.org. Email me your questions, that's perfectly fine. I'll try to respond. Sometimes I don't respond promptly because I don't read this email every day, but within a week you might expect an answer. Also, if you are at a co-op and you would like me to provide this analysis for you, you can contact me and we can have a discussion about that. I hope you have a good rest of the day.